All right, so let's go over some of the properties that you were thinking about, reviewing from Calculus 1. I did happen to see that a lot of you were thinking about integrals in terms of the area under the curve. And certainly that is super duper important. The area under the curve interpretation. You've got the graph of your function, y equals f of x. Here's the x-axis, here's the y-axis. A and b are some numbers on the x-axis. Maybe a is here and b is to the right of a. So a is less than b, which is the same thing as saying b is greater than a. And geometrically, you're trying to find the area under the curve. Now, for some people who like geometry a lot, that might be good enough. I just want to know the area under the curve. But for other people, that might not be good enough. You know, what's it for? Why would you care about an area under a curve? And one of the main things we're going to emphasize starting Wednesday is that the area under a curve has a lot of applications besides just plain geometry. A lot of applications to physics, applications to probability, applications to finance that we're going to talk about as the semester goes on. So it's not just a geometry problem. Okay? But that area does equal, when the graph again is above the x-axis, the thing that we call the definite integral. The definite integral of the function from x equals a to x equals b. A is called the lower limit of integration. B is called the upper limit of integration. In 99.9% of problems, A is less than B. Though on Wednesday, we will talk about the fact that you actually can give meaning to this even if it's the other way around. Even if A is greater than B, you actually can still give meaning to this. But this does beg a question. How do you figure out what the area is? I mean, it's one thing to just write down a symbol and say, hey, that's the area. But how do you figure out what it is? What's the main theorem to use to figure out what the area equals? It's got a name. Do you want to say? Fundamental theorem of calculus. Fundamental, sounds pretty important. Fundamental theorem of calculus, or FTC for short. Now, there's an equation that's the most famous part of the fundamental theorem of calculus, and I will write down the equation, but you should realize as a theorem, it's more than just an equation. It's what's called an implication, an if-then statement. If something's true, then something else is true. Let's say it this way, if something's true, then something else is guaranteed to be true. What's the if part? If little f is a continuous function on a certain closed interval. How about the interval from a to b? If I write a comma b with square brackets around it, that is standard notation for the closed interval from a to b. This represents the set or collection of all numbers between a and b, including the endpoints. I want to get used to that. There's something called set builder notation that allows me to describe this in another way. I use curly braces for sets. The set of all x, set of all numbers x, such that, I'll put a vertical line which stands for such that, or with the property that a is less than or equal to x is less than or equal to b. That's called set builder notation. These are just two ways of describing what X can be. X has got to be between A and B, possibly including A and B. Well, the set definitely includes A and B. And if capital F has another property, has the property that, what do you think I'm going with this? Do you remember? There's a hint, capital F prime. What's going to be true about capital F prime, the derivative? Little f is going to be the function I'm integrating. Yeah, capital F prime equals little f, lowercase f. Over the entire interval, I should really be a bit more specific here. Capital F prime of x equals little f of x for all numbers x in the interval. Here's another notation I'm going to introduce. This funny looking E is really a Greek letter epsilon, means in the interval, or is an element or number in the interval. So those are my hypotheses for the theorem. The conclusion comes after the word then. Then I can evaluate the integral of little f by taking capital F of B minus capital F of A. Right? You've seen this before. If you took Calc 1, you've seen this before. You've used it before. One more little bit of notation. Sometimes this difference, capital F of B minus capital F of A, is written this way with a capital F of X, and then a vertical line that in this context means evaluate at A to B. This vertical line means such that, this vertical line means evaluate at. It's just a shorthand notation for this difference. That's all it is. Nothing magical. And in fact, usually when you're doing definite integrals, you write this kind of thing first to remind yourself what you're doing, and then you write that. So the notation is nothing magical, but the theorem itself should feel kind of magical. You want to find the area under the curve, under the graph of little f? Just do that. Done. Poof. Out pops the answer. Like, what? Why? Why in the world would that work? I want to try to get to the point, hopefully in the next 2 weeks, but for sure in the next 3 or 4 weeks, where this equation is intuitive to you. It makes intuitive sense. Not just that's what to do, but it even makes sense. I'm not saying it's easy. Newton and Leibniz were the first people to figure this out 350 years ago. Before that, nobody had figured this out. So it took their genius to figure this out, to have the intuition to figure it out. They actually didn't prove it. They didn't have modern methods of proof that we have developed in the last 150 to 200 years mostly to be able to rigorously prove this without a shadow of a doubt. But they had intuition. It made sense to them. But to us right now, it just feels like magic. Here's an example. Let's say you wanted to figure out the area under the first arch of the sine function. So the graph of sine of x, its first arch looks like this. And then it does keep repeating. It goes down, it's got an arch that goes below, and then it keeps going on forever and ever in both directions. But what if our goal was to find this area right there? What does that area equal? You might wonder, since trig functions have so much to do with pi, maybe the area is pi, Or maybe it's pi over 2. Actually turns out to be simpler. You can use an integral in the fundamental theorem of calculus to figure it out. You have to figure out what that number is. What is that number? That should be memorized. That x-intercept right there. What angle? So sine of 0 is 0. What angle gives you 0 again? Pi radians, or 180 degrees. You want to use radians in calculus. So that area is going to be the definite integral of the sine function from 0 to pi. I can use the fundamental theorem of calculus. The little f of x is the sine of x. So I need a big F, a capital F. I need an antiderivative of little f. By the way, it's fine to say antiderivative too. I usually say antiderivative. What's an example of an antiderivative of little f of sine of x here? Is it cosine? It's actually negative cosine of x. Why? Well, careful. The derivative of sine of x is cosine of x. But the derivative of cosine of x is negative sine of x. And that's the reason an antiderivative of sine of x is negative cosine of x. This is because the derivative of cosine of x is negative sine of x, or if you prefer, the derivative with respect to x of negative cosine of x equals sine of x. I'm not done yet in this line because definite integrals are numbers, and that's not a number yet. I need to put the evaluate symbol at. X goes from 0 to pi. Now, it might feel in looking like this that we're going to get a negative answer, and wait a minute, how can this area be negative? But we won't. It's going to end up being positive. You got to be careful. Again, this notation here with this evaluate symbol means it's just shorthand for f of b minus f of a, where capital F is this function, negative cosine of x. So I need to do negative cosine of the first number, negative cosine of pi, minus capital F of a minus negative cosine of the lower number, minus negative cosine of 0. Very easy to make a mistake here, right? You could easily make a mistake with these signs here. And yeah, it looks like it's going to be negative, but no, cosine of pi is -1, so we get a negative of a negative, which is positive. And here, two negatives make a positive, and cosine of 0 is 1. So the answer is 1 plus 1 is 2. And that is the area of this first arch. Exactly 2. Not 1.999, not 2.001, exactly 2. Pretty amazing. Depending on your view of what's amazing or not. I think it's amazing that it turns out to be such a nice number. Is it right? Here's a point, here's an example where we should spend 30 seconds, say, at least, asking ourselves if this answer seems reasonable. This is supposed to be this area. I'm not going to be able to check that's 2 exactly without doing exactly what I just did, but I could see that 2 seems reasonable. For example, if I put this arch inside this rectangle, I realize the area of the arch has to be less than the area of the rectangle. The area of a rectangle is base times height. The base is pi. What's the height? 1. Graph of the sine has a maximum of 1. So the area of that rectangle is pi times 1. Pi. About 3.14. Don't ever say pi equals 3.14. It's just approximately 3.14. But 3.14 is certainly bigger than 2. 2 is less than 3.14, which it has to be. You can see it from the picture. Moreover, the shaded red area is more than half the area of the rectangle. Half the area of the rectangle would be pi over 2, about 1.57. Yeah, 2 is between 1.57 and 3.14. This is reasonable. You can also use your calculator. Go to your y equals screen, plug in your function, in this case sine of x. Make sure you're in radian mode. Mode here is radian mode. If you're in degree mode, switch to radians for calculus. The only way you'd ever use degrees in calculus is if you've got a problem involving a right triangle that's phrased in terms of degrees. Otherwise, use radians as default. The derivative of sine of x when x is in degrees is not cosine of x. It's only true when x is in radians. That's why radians is so special. Anyway, go to your y equals screen, plug in sine of x. 0 to pi. I can make my x scale, say, for example, pi over 4, for example. Y going from -1 to 1 is fine. Graph it. There's that first arch of the sine function. Go to the calculate menu above the trace button here on mine. And number 7 is an integral. The lower limit of the integral is 0. The upper limit is pi. Calculates the area to be 2. There it is. Mathematica is pretty simple with this kind of problem. Make sure you get your palettes. Actually, you can do it without the palettes, but it's nicer with the palettes. Palettes menu. I've got the writing assistant up, but any of these first 3 will work. And under typesetting, once you've got a line there, you make sure you press the integral button, which is right down here. Press that button. Goes 0 to pi. Pi can be capital PI or it can be escape, P escape. You have to capitalize the sine function, not the entire thing, but just the first letter. And put the x inside square brackets, not parentheses. Do a shift return to enter that once the cursor is on that line, and there the answer is 2. You can do it without the palette. You can just type integrate with a capital I, like this. Oops. I must have a different f of x, sorry. There we go. Integrate will integrate as well. And here is the interval to integrate over. So the fundamental theorem of calculus is very useful to do integrals. Is there ever a problem with it? Could there ever be a problem in using it? Yeah, if f is not continuous, that could be a problem. Though sometimes that problem can be gotten around by integrating f over the pieces where it is continuous and adding the results together. It also can be a problem if you cannot figure out what capital F is, right? You got to be able to figure out what capital F is if you're going to use this. In the case of little f being sine of x, capital F, by knowledge about derivatives, is negative cosine of x. But what if we were integrating sine of x squared? Sine of x squared. What does Mathematica say for the answer, say from 0 to 2? Says the answer is square root of pi over 2 Fresnel S of 2 times square root of 2 over pi. Huh? What in the world's going on there? The upshot of this is that's a really hard integral to do. That's one answer with the fundamental theorem of calculus, unless you define a new function called Fresnel S, which evidently somebody named Fresnel did. If there's a Fresnel S, does the S correspond to the sign? Is there a Fresnel C? If I use a cosine? Yeah, there's a Fresnel C if I use a cosine. So somebody named Fresnel came up with this function, Fresnel S and Fresnel C. And if you know that function, then you can do the integral. That's kind of weird. Okay, we'll talk more about that later. Some more properties that are worth writing down. There's something called linearity. Linearity is what that says. The integral of f of x plus g of x is the integral of f of x plus the integral of g of x is one example of linearity. I'm going to write a more general equation. The integral of a sum, f plus g, is the sum of the integrals, the integral of f plus the integral of g. You can also put a minus sign instead of a plus. You can also have more than two functions. In general, you can write this. The integral from a to b of, say, c1 times f1 of x plus c2 times f2 of x plus dot, 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 plus cn times fn of x. The integral of that combination of functions, in fact, this is called a linear combination of functions. A linear combination of functions is the corresponding linear combination with the same c's of the functions themselves. In other words, of the integrals of the functions. In other words, it's the first constant, c1, times the integral of the first function, f1, plus the second constant, c2, times the integral of the second function, f2, etc. The pattern continues, is what the dot, dot, dots mean, plus the last constant, cn, times the integral of the last function, fn. This is actually a very important property of integrals, though we don't typically use it that much in this class, explicitly as it's stated. But it is actually very important in higher level math, where you use the integral as something called an integral operator, which I don't want to get into. It's related to stuff in physics, including like quantum mechanics and stuff. And by the way, calculus, even though you don't see it in the class, is essential for the way the world is today. For example, modern communications and computing technology is not possible without calculus. I'm telling you the truth. It's not possible. Calculus is essential for making modern technology work. For one thing, to even understand quantum mechanics, which is also essential. So even though we won't use this a ton, you should know it and be able to apply it. Most typically, n would be 2. You'd have 2 functions and 2 constants. And even most typically, you might say C1 and C2 are both 1. So you're just adding 2 functions. A fourth property, which is what we'll end with today. There are more than this, but we'll end with this one today, is what you might call a property of endpoints. Property of endpoints, or endpoint property, something like that. You can take any definite integral and break it up into the sum of 2 integrals. If this is the integral from a to b, you can write this as the integral from a to c plus the integral from C to B, where C most typically is an arbitrary number between A and B. So it's not in alphabetical order here. If A is here and B is here, C can be any number between A and B, like maybe there. And geometrically, what this is saying is the area under the curve from A to B can be broken into two pieces. The area from A to C plus the area from C to B. That's what those integrals represent. So it makes intuitive sense in this case when C is between A and B and when the graph of f is above the axis, so you can think of the integral as being an area. But this is actually still true even if C is not between A and B, and even if the graph of f goes below the axis, it's still true. However, to see that it's true in those cases, you have to talk about how to interpret integrals both that go below the axis, and also what happens in an integral if the lower limit A is bigger than the upper limit C. How do you interpret such an integral? You actually can interpret it. You can give it a consistent interpretation, and this still works. We'll talk about that more on Wednesday. Okay? All right. Have a good day.